Last time, we learned a good set of mathematical tools that are particularly handy, actually, when dealing with Fourier transforms. We also then came across a set of key results as we build up our physical theory upon our underlying mathematical framework. Now, in terms of the mathematical tools that we learned, there was a series of generic tools about, how you manipulate integrals and so forth. But then there were certain key results that we found. One was this particular integral, which then we learned actually gives us a good representation of the Dirac distribution. Now, I've written here in very light letters some little extra detail, and this had all to do with our argument about putting in a convergence factor that won't affect the physics, but which makes the math happy. And the result of that actually was a Dirac distribution. The width of that distribution actually is controlled by this parameter epsilon in ways that we had seen. It really is just that this epsilon actually gives us the half width of the resulting delta distribution. From a practical point of view, after all the logic that we gave last time, the practical bottom line lesson is that once you ever see an integral like this, you don't need the extra convergence trick, right? If you ever see an integral like this when dealing with Fourier transforms, you can safely replace it with an idealized Dirac distribution. Next, we learned a bit about how to integrate over functions when there's a delta distribution within your integral. Here's a basic sketch of what's going on. The basic bottom line lesson was that, well, the peak is located at a particular value. And if we look at the integrand, which is the product then of some smooth parts, say this function f of x, and that peak, of course, because the peak is 0 everywhere, most of the function f of x would be multiplied by 0. The only portions of that function that really matter are this tiny little portion that exists within that peak. And within that peak, because we are making its narrow so tiny, something like down on the Planck scale or some minimum length scale in the universe, we can be assured then that the function itself appears at that scale to be a perfectly smooth and continuous function. Consequently, to whatever level of approximation we might like to work by simply making epsilon mathematically smaller and smaller, we can be assured that a very good approximation for our function f of x is just its value at that peak f of a. So we can make that replacement of f of x with f of a without changing the value of our integral, because again, at all other points, the peak is giving us 0. Once it's a constant, though, it can be pulled out of the integral, and then we're just left with the integral that tells us the total area under that peak. And because it is a Dirac distribution, that area is just 1. And so we finally get just then the value of our smooth pieces of our function evaluated at the location where the peak occurred. Now, as part of that chain of argument, I reference the fact that this function f of x I am taking to be a continuous function. And the reason why I'm doing that is that I'm again thinking like a physicist, right? My main point here in the course has been on these mathematical issues of singularities. There are no things in this universe that ever, practically speaking, ever turn out to be exactly 0 or exactly infinity, because infinity is really 1 over something that's exactly 0. And also I claim that likewise, all discontinuities are really just mathematical idealizations, something like a point mass or something along those lines. So for example, here's a typical function that you might think has a discontinuity in it, right? We could think of a discontinuous function. But what that means is the function undergoes a sudden change at exactly a precise point. And what I'm trying to convey is that physically speaking, in order to generate physically a function that would have this kind of behavior, there would have to be some sort of an effect that is localized, strictly speaking, at that exact point. For example, you might be thinking about the strength of the electric field, and it can be ideally discontinuous if you have a perfect infinitesimally thin sheet of charge located at this point. But by Heisenberg, that sheet of charge can never be localized, strictly speaking, at an exact point. Therefore, the charge distribution actually would kind of be smeared around because of the probability distribution of the location of your sheet, and your function then would be continuous along the scale of how well I can actually localize a sheet of charge. There's another way we can look at this. So not only do I argue that from a practical point of view, any function really viewed down on that Planck scale has to be continuous because we can't have a cause for the discontinuity that is localized to better than that scale. My other argument to you would be something like this. Okay, suppose actually the functions we're trying to deal with here actually are discontinuous. I argue that there can be no cause that would do that. But say you do give me a function like that and I have to do my mathematics with it. Well, here's the next argument I would make. I would say, okay, well, let's take that localized point and let's make a tiny range around it on the size of the Planck scale. And then within that range, I'm going to replace the function you gave me with a function that actually is continuous, right? But it's going to only have that, the whole discontinuity is going to happen within the range of that Planck scale, right? So I'm going to have a different function from yours, but mine now is perfectly continuous. Now here's my other physical argument. The entire difference between these two functions occurs within this Planck length scale. No physical influence, right, nothing in the universe outside of that distance can depend upon anything that happens within that distance. Because to see what's going on within that distance, as we discussed, generates so much energy at that point, the whole thing is swallowed up by a black hole, right? So that means anything we compute from either your function or my function will, physically speaking, be indistinguishable. So we're going to use my continuous function so that I can do all of my mathematics, but I know from a practical point of view, nothing can depend on the difference between your true discontinuity and my smoothed over discontinuity, right? So that's my second argument on that. Very good. So now, back to the results that we learned from using such techniques. We found, in fact, that what we have are two equivalent representations for our quantum state. There's, of course, our basic description in terms of psi of x, but equivalently, we can express psi in terms of this set of weights, which are really whose Fourier transform gives us psi. This Fourier transform, now we gave a precise mathematical definition. It is a superposition of some quantum principle of superposition weights, which we are calling psi tilde, times then the pure states of the corresponding observable, and we learned that this is the proper way to normalize your pure states of momentum p equals h bar k. And this particular operation is known as the Fourier transform, and that is how we shall define it with this particular choice of normalization. If we make that choice of normalization, we then proved that the actual value of these weights can be computed directly from knowing our original wave function. Following this integral, which again comes with this particular normalization, and we will be calling this particular operation the inverse Fourier transform. Now the point here is that these two functions contain equivalent information because from one we can always derive the other function. So we really now have two different representations for our quantum states, which are equivalent to each other. This particular representation is known as the position representation. And this representation is then known as the momentum representation because it deals with momentum. Finally, the key point of all of this is how we actually predict the outcomes of all possible experiments, which are our probability distributions of our two key variables for point charges. And we now have an explicit formula for the probability of finding the particle at x. It is given just exactly by the square of our wave function. For the probability of observing different momenta, we learn now that this is just then proportional to the magnitude squared of the Fourier transform, the psi tilde, the momentum space representation of our wave function. And this second case then gives us a particular case of our general considerations under the general quantum principle of superposition, because we've now learned that the way we interpret the weights in such a superposition is that the square of those weights gives us our probability. So if we had some general observable, maybe not momentum, there would be a probability function that describes its distribution. It should be then proportional to the square of some Dirac quantum principle of superposition weights, and those weights states then, when added up times pure states of my observable, would then recover for me any general quantum state that I might want to think about. And this probability then comes as a proportionality, and it of course would then have its own proportionality constant, which then is to be determined. So our current focus now is going to be to try to understand what choice we should make for alpha so that we can deal properly with our momentum probability distributions.